Let's delve a little bit deeper into disc brake wheels and see what happens to spoke tension when we brake. Now in the next number of slides you'll see graphics that start with this representation here, and let me point out something to avoid confusion. That line there represents the horizontal axis of the wheel, and this represents the vertical axis. So again, these four lines here do not represent radially laced spokes. They're there to give you a sense of the size of angles. Here's a graphic to try to illustrate what it is we're dealing with. So there's our wheel. There's our 164 newtons of stopping force. And there's a hub. There's the disc. There is the hole-to-hole flange diameter. And let's say we have a radius of 21 millimeters, which might be typical. So in order to stop the wheel from rotating forward, these spokes here have to pull the wheel backwards and slow it down. We're going to initially work through this calculation as if all of the stopping force had to be applied with one spoke, and then we'll spread it out to all of the spokes. Here's a little trigonometry. That is one of our spokes that has to stop the wheel, and that is the distance from the center of the hub to the rim. That is the horizontal component of what the tension vector is going to be. If this is a 290 millimeter spoke, then that is 21 millimeters. That gives us an angle here, theta, of 4.14 degrees. Now, my lateral component of the tension vector there shown at the hub is the same as if I show it here at the rim, and that is going to have to amount to 164 newtons. The spoke shown here will already have tension on it as part of a strong, stable wheel. As the wheel stops, the tension on that spoke will increase. So my question becomes this: how much does the tension of the spoke have to increase to yield an increase in the horizontal component of the tension vector of 164 newtons? So my sine of theta is equal to the tension that develops on the horizontal component divided by the total tension vector, which is increased. And I get that expression here substituting 0.072 for the sine of 4.14 degrees, which gives me this. And I find that my increase in total tension is going to be 2,278 newtons. My change in tension for each spoke is going to be 2278 newtons divided by the number of spokes. If I have a 24-spoke wheel, I divide 2278 by 24 and I get 95 newtons. And that's about 10 kilograms of force if you prefer that measurement of spoke tension. Now, using this nice Shimano XT hub as an example, we can see that the non-drive side flange has been moved inward to accommodate space for the rotor, and that means that the center of the hub is pretty much equidistant between the two flanges. It's not exactly that, but it's pretty close. The actual center of the hub is here, but if I assume I can move it just a few millimeters to the left, it will simplify my calculations. We're going to say that these two distances are the same, and so are these two. In this diagram here, which is obviously not drawn to scale, the rim is centered directly over the middle of the hub, and the spokes on the non-drive side and the drive side will have equal angles leaving the rim, and the tension on all of the spokes will be the same. Let's make a little table showing static tension expressed as newtons or kilograms of force. And over here, dynamic stopping tension expressed with the same units. And under each of those, we'll subdivide into two more columns for pulling spokes and pushing spokes. Under static tension, I know that my pulling spoke tension and my pushing spoke tension will be the same, and typically that could be 1176 newtons, which is also 120 kilograms of force. Under dynamic stopping tension, when I stop the bike, my pulling spoke tension will go up by 95 newtons or 10 kilograms of force, giving me these units, and my pushing spoke tension will go down by the same amounts, giving me those units. You can work out the solution to these problems either by the system of trigonometry I showed you or by the turning moments that we measured earlier. I think the turning moment system is a little bit easier because all I need to do is measure big R and small r, and I can work out the forces from there. Let's work out another example and change the scenario by having the rider going down a hill. Here is a similar situation. Same rider, same bike, same velocity, and the same amount of total kinetic energy. And if I were riding at 0 degrees, I would have the same amount of acceleration formula as before. I would come up once again with a negative 2.98 meters per second squared to stop the bike on level ground. But the bicycle is not on level ground, it's going down a hill, and so I'm going to have some amount of acceleration due to gravity that I have to counteract to stop the bike. If the bike were falling straight down like a rock, that amount would be a full 9.81 meters per second squared, but it's not going straight down, it's going down a 10-degree grade, so I multiply that number by the sine of 10 degrees, and I find that I have an additional gravity component to overcome of negative 1.70 meters per second squared. When I add those two together, I get a total acceleration of negative 4.68 meters per second squared, necessary to stop the bike on its descent. Just a quick reminder of our situation. We have a bike and rider with a total mass of 110 kilograms, riding at 8.94 meters per second with kinetic energy of 4.44 times 10 to the third joules, and we're going to turn kinetic energy into heat in 3 seconds. My stopping force is still going to be that same equation, mass times acceleration, but the acceleration term is larger, and I multiply that out, I get a negative 515 newtons. Now, it's even worse than that because as I brake, my body weight is going to pitch forward. I'm going to end up putting considerably more of the responsibility to stop the bike on the front wheel than the rear. And I'm showing here a typical about 2/3 on the front and 1/3 on the back. So my stopping force on the front wheel has suddenly gotten pretty large. Here is our 345 newtons of force. If my typical wheel with a tire on it has an outside diameter of 640 millimeters, then big R is going to be 320 millimeters, and small r, we'll use the example we used before, is 21 millimeters. And when I divide that out, I get a braking force at the whole flange diameter of the hub of 5,257 newtons. The change in tension for each spoke will be 5,257 newtons divided by the number of spokes. If I have a 24-spoke wheel, the change in tension for each spoke is going to be 219 newtons, or 22 kilograms of force. There is no change in my static tension. We see that my dynamic stopping tension changes quite a bit. The pulling spoke is increasing to 1,395 newtons, or 142 kilograms of force, and the pushing spokes decreasing to 957 newtons, or 98 kilograms of force. I will show you some pictures of wheels, and then we'll work out one more example. We can use this bike here as an example. This is a specialized 2015 Cirrus Comp disc brake bike, and we have 32 spokes in the rear, 28 in the front. There's a close-up of the front wheel, and this wheel set has a mass of 1,950 grams. You can't really see it from the picture, but both sides of the front wheel are tangentially laced for torque transfer. Now we're going to take a look at the front wheel of a different bike. This is a 24-spoke front disc wheel. Here we see it from the disc side, and here we see it from the non-disc side. This is the forward direction of the wheel. Now, very unfortunately, on the non-disc side, these 12 spokes here are radially laced. As such, they are incapable of transferring torque, so that I really only have 12 spokes out of the 24-spoke wheel that can help stop the wheel from turning when the disc brake stops the hub. These are the tangentially laced pulling spokes. These are the tangentially laced pushing spokes. If we go back to this scenario with this rider and disc brakes, this part of the calculation is identical to what we had a few minutes ago. But here we have to divide by 12 instead of 24, so our change in tension will be twice as great. The static tension figures are still the same. But if we look at our dynamic stopping tension, we see that the rise of tension on the pulling spokes is quite large. This is an example of a wheel that failed, and the symptoms that you'll see here fit exactly this scenario that I'm concerned about. It's a rear disc brake wheel, and we're looking at it from the drive side with the cassette having been removed. So this might be what the wheel would look like if the cassette were on it. But by taking the cassette off, you get a better view of the spokes. When I accelerate the bike by turning the hub clockwise, the tangentially laced spokes, these 9 on the drive side and these 9 on the non-drive side, will increase in tension as they try to pull the rim clockwise. When I apply my brakes to the rotor, the hub stops moving, and the spokes shown here, which are also tangentially laced, try to stop the wheel from rotating clockwise. The blue spokes are on the drive side and the red spokes on the non-drive side. Earlier we made a little simplification, and we assumed that when the rim was centered over the hub, these distances would be the same, and so would these between the two flanges, and that would give us equal tension on the spokes on the drive and non-drive sides, and that would make these horizontal components, of course, equal also. But in actuality, for these two lines to be equal, which means that the rim is going to be centered over the hub, this line here has to be shorter than this line so that the center line is closer to the drive side flange, which means that this tension vector is going to be longer than this tension vector in order for the horizontal components to be equal, which they always must be. So this shows that the drive side tension will be higher even in a disc wheel than on the non-drive side. Maybe not as much greater than is indicated in the graphic, but greater nevertheless. Because this is a rear wheel, the static tension on the drive side spokes will be higher than the static tension on the non-drive side spokes. The 18 blue spokes on the drive side will have a higher average tension than the 18 red spokes on the non-drive side. If I want to consider which group of spokes will have the highest tension at any point when I'm riding the bike, either accelerating or stopping, it's not going to be the spokes on the non-drive side, since they start at a lower average tension, so I can immediately dismiss those. The tension on these 9 spokes here, these pulling spokes, will increase when we accelerate. but we're going to dismiss those also because they will not increase as much during accelerating as the other 9 spokes do when braking. So these 9 spokes here are the ones that are going to have the largest dynamic tension on them of any spokes in the wheel at any point in time. And when I examined this wheel carefully, I found that the rim had cracked where every single one of those 9 spokes that are trying to stop the wheel when I apply the disc brake, those 9 spokes have cracked the rim at those points. The rim had cracked longitudinally at each of those locations. This happened to be the worst one. This is not a bad rim. It's a double wall rim. At 511 grams, there's enough aluminum in it that it should have been able to be strong enough. Here's a close-up of the crack, and it would have started with this longitudinal crack here and then progressed from there. There's a hairline crack here, which you might be able to see. Now, this is a small crack, but it still represents a significant weakness in the rim and will only get larger over time. By looking at the rim from the back, we can see that there's no crack in the inner wall here. The only place that the rim cracked is actually in the spoke bed where the tension is concentrated. The information I've just provided you is not dispositive, that is, it does not prove the point, but it is evidence of the concern that I am pointing out. And we will continue to explore this in the next chapter.